Oops. Oh, gosh, I was testing my audio and I did not get these. Let me see if I can do this in one go. Can't do that. Oh, okay. I can't do that. That's okay. Oh, I'm not screen sharing, am I? Why don't we remedy that? Screen share, and that'll be Adam. Okay. I hate it when it does this. Okay, finally. So we've got a small variety of topics to cover. Let me blow that up a bit. Today we're going to be talking about list methods and operations. We're going to be going over while loops. So this is similar to the for loops concept that we talked about in the previous lesson. We'll also be talking about strings some more. So I know I've introduced the idea of strings before. We've talked a little bit about them. But today we're going to just dive in a little deeper. So quick overview. Let me just get this up. Okay. Quick overview. We've talked about data types, abstraction, control flow, and iteration. Now, I went over this. I've gone over this at the beginning of every class. I went over this. I also had another category that I've been omitting kind of strategically because we sort of covered what we're going to cover on it, which was evaluation slash execution. So, this is my own sort of schema, and it is my opinion. But in my opinion, these are basically the things you need to know, sort of the major categories that you need to know when you're approaching a new programming language to get started in that language. And these are the things that we cover in Python. So that's the context for what this is and why I've been doing this. This is by no means every category in that you could imagine in a programming language. This doesn't get into like development patterns and workflow stuff and like coding paradigms like object-oriented or functional programming. This doesn't get into any of that, but whatever you decide to do and choose to do and find yourself doing in your programming career will be, may not involve only these things, but it will be in one way or another founded on these things. It'll be predicated on these things. So evaluation and execution, this is just kind of language detail stuff like interpretation versus compilation. Python's an interpreted language. Typing system, how things acquire and change their types. How are they allowed to change their types? And Python has a really flexible kind of do what you want typing system called duck typing. So that's what this category is about. And like I said, we've kind of just covered that, and I'm taking those concepts as just sort of givens. So I've been omitting that one. Data types. Let's just look at the data types we've covered. We've covered int, float. These are our numbers. Bool, string. Oops. Oh, come on. Oops. Sorry, I lost my thing there. Okay. We've covered int, float, bool, string, none. I always feel like I'm forgetting one in there, but I guess that's what we've covered. Then we've covered lists, and we're going to talk more about these today. And the reason I'm just making a little separation there is these types are immutable, and lists are the only mutable type that we've talked about thus far. We're going to be talking about two other mutable types that are built into Python as well, but later in the course. Abstraction, variables are a kind of abstraction. Functions are another kind of abstraction. Control flow is if, elif, else. Three simple keywords that go together to make potentially somewhat complicated logic, but the foundations are simple. And then iteration. So we talked about for loops and while loops. Oh, excuse me. We talked about for loops. Today we're going to also talk about while loops. So there are other forms of iteration other than these, but these are what we're going to treat as the two primary tools. You can solve just about any problem with these two. Actually, any problem that you can solve with a for loop, you can solve with a while loop. Not so much the other way around. But the reason we teach for loops first, even though they're a little less powerful, most problems that most programmers are going to face in their daily life can be solved with for loops. There's certain, niches in coding that maybe require a certain kind of problem solving that leans into or makes more use of while loops. But in general, most of the time you can get away with using a for loop. And for the slightly smaller set of problems that for loops are capable of solving, they are slightly faster. So Python can optimize certain things under the hood for for loops, and they are easier to deal with. They're easier to read, they're easier to write, and they don't get into infinite loops unless you really, really work really hard to make a for loop get into an infinite loop. In a little over 2 years of helping students here in this job in one capacity or another, I've seen somebody write an infinite for loop on accident once, whereas I occasionally write infinite while loops because it's easy to do. You'll see when we get into it. So the trade-off here is for loops can be used in most circumstances, with the little asterisk behind that, right? Quote unquote most circumstances, and they make your life easier. They make Python's life a little easier. They can potentially run slightly faster. And when I say slightly faster, I mean just slightly faster. Not like, it's not like 10 times or 1,000 times faster or something. It might be like a couple, maybe 1% faster. Whereas while loops are slightly more powerful in terms of they can solve a wider variety of problems, but they burden us as the programmer they give us more control, but they also burden us with that control, so that we have to kind of manage them a little more, and we'll get into that. So I just wanted to spend a little time on the overview today to mention, you all have got basically a complete set of tools at this point. Um, you've got a number of types to work with. We haven't gone over all the types that we're going to go over. You've got 2 of the 3 major abstractions. The other one left is classes, and we're just going to have one lecture on this in Premium Prep. We're not going to dive deeply into object-oriented programming at all. But you can feel free to do that on your own time. Classes and object-oriented stuff won't be on the TI. They will cover some of that in the DSI. So we just kind of leave that to you to do on your own, and the DSI to kind of get into object-oriented stuff. But classes are there, and we'll kind of touch on them later on in Premium Prep. Control flow, this is it. In Python, like, that's the whole story. There aren't like formal switch case, if you're familiar with another language that has like switches and cases and other match, other control flow things. Python just has if, elif, and else, and the rules in terms of how these relate and kind of how they go together are a little complicated, but basically, like, we've covered that, and that's all there is to it. And from there, it's just a matter of just practicing your control flow stuff and getting good at it. And then iteration, and these are our 2 primary iterators. So that's it. That's a complete set of tools. You can now start solving any problem that you want. It's just, from here on out, it's a matter of just practicing all these things together and kind of grinding away and learning patterns and like memorizing kind of little rules of thumb for little specific circumstances, and basically a lot of like vocabulary and just repetition practice stuff. So the vocabulary stuff is mostly going to relate to learning the data types. So from here on out, the work is, in my opinion, mostly in data types. Cool. All right, so let's jump into list methods. So I've got, let's do this. Nodemon watch everything and execute IPython 3. And I want to go to source Python main. There we go. And just do a little sanity check. Good. Okay. Always good to test your environment, before you get too much into things. Let's do that. All right, so this is a list of list concepts, and this has some various functions as well as methods in here. I want to show you a little trick. Anytime, and this actually relates perfectly to exactly what I was just saying when I said the work that's left over is just kind of in grinding out an understanding of data types. This is going to be like a really good tool to help you do that. So you'll come down to, you could do this in your Replit terminal, or if you're in a local terminal, you'll start an IPython session. IPython3 for me is the command. Your command might be slightly different because I'm on Linux, so who knows. Oh wait, we got a question. Can I minimize or move? Wait, the recording info window into the background? Recording info. Minimize OBS? You guys can see OBS? Can you guys actually see the OBS window? You don't see it anymore? That's so weird. Huh. Interesting. I'm not sure what that's about. Is it back if I do this again? Sorry, that's a really strange problem. You guys don't see it? Okay, I don't know what that was about. For me, all I'm seeing is that it's presenting the Atom window, but I don't know how it would be showing you OBS. Okay, sorry. Let me know if that comes back up again, and well, I'll try to solve it. Okay, anyways. So, back onto this. So when you're learning a new data type, you can start up an IPython session, and there's a really handy, there are two really handy functions. First one is dir, and the next one is help. So dir is short for directory, and we actually need to print out the directory in order to be able to see it. So we'll say dir, and we'll just pass into dir, we'll just pass it the data type we're curious about. So anything, in this case, excuse me, gosh, in this case, we're curious about a list, so I can just pass it a list. I could do the list keyword, list, or just an empty list, or like a variable that evaluates to a list. It can have like anything in it. It doesn't matter, just so long as it's a list. So just pass it the thing that you're curious about, and it'll give you the directory of that thing. For now, so it shows you all these what we call dunder methods. They're called dunders because they begin and end with a double underscore, so it's double underscore add double underscore. So we're not going to get into these. We're gonna sort of touch on these in the lecture about classes. If you want to learn about these, I'll leave it to you. You can search for what are Python dunder methods. You can Google that on your own time. The important ones to look at for any data type are going to be the undundered methods, the regular named methods. So that'll be these ones here. Okay. So this list is not everything that's in this list. But it's most of it, and we'll go through this other list as well and kind of pick up what we don't cover here. But anytime I go learn a new type, or I want a refresher on what methods are available for that type, I can do this, and that'll help me. And then another really useful tool is, say you see one of these methods that you're curious about, say insert, and you're like, oh, I wonder what insert does. You can do help, and help is a function, so it takes parentheses, and then just pass it the thing you want help on. So you could pass it a list, or you could do list dot insert. Now, if you pass it a function or a method, you do not put the parentheses on the method like that. You leave the parentheses off, which is weird. You usually don't do that. In this case, you need to leave the parentheses off, otherwise you'll get other weird stuff. So we'll just do help on insert. This tells us insert takes in is a method that takes in an index and an object. Slash just means that it's a method of something. This tells us it's a method of built-ins dot list, so it's a list method. Insert, or it says instance, method of built-ins dot list instance. And then this is just a little description where it says insert an object before the index. So it'll take this object and insert it before that index. well, I think about it as inserting it at that index, but whatever. So most or a lot of help docs will have more copy than this. This is like a really short one. But yeah. And then for me to exit out of this, I just hit Q. For most of you, it'll probably be Q to exit out of the help docs. And you can, this is a way of accessing the internal documentation for anything. So I could do help for the len function. We briefly looked at the len function before. So len takes in an object and returns the number of items in that container. Cool. Okay. So those are really useful tools as you go about learning new types. You're going to learn new types basically based on, I mentioned this a few times before, but in any type you want to know obviously like when and where to apply it. So kind of the description of it and its applications, what it's useful for. Obviously integers and floats are useful for doing mathematical operations and quantifying things, whatever. Booleans are useful for gating conditions in control flow, keeping track of systems that have two states or whatever. Strings are useful for holding a set of characters or holding a string of characters, representing text and dealing with the characters of text, right? Etc. So that's one aspect of it. And the other aspect of understanding types, in addition to the description and the application of them, is what tools are available for them. And what I just showed is a good way to start getting a sense of what tools are available. So all of these tools apply to lists. These are built into lists. So let's just go down the line and play around with each of these and talk about each of these. Yeah. So appending. So remember to start a new list, we'll just say we'll create a variable. I'm going to call it LST for list. Again, I'll remind you, don't use LIST since that's the built-in type specifier and the function name that's built into Python. Python will let you do this. I wish it wouldn't, but it does. So you just have to remember, don't use LIST, use LST when you're making a variable. Or you could call it poodle face, whatever you want to call it. I'm going to call it list because that's what I like to do. So if we want to use the append method, so remember a method is very similar to a function, except it's built into some data type. It's like it's like a feature of that data type. It's like a function that's built into that data type. That's an overly simplistic description of a method. There's a little more to it than that, but I don't want to overload you all. For now, if you see something that looks like, some data type dot something, and then you have parentheses after it, that's a method. For now, you can think about that as a method. Okay, so we'll say list.append, and this is going to add something into the right-hand side or the end of the list. So if I say hello, oh, probably ought to print it out. List. Okay, we've got hello. Let's just do it again, and then I've got two hellos. So however many appends I run is as many elements as that append is gonna as append is going to add. Whatever. I think you see what I'm trying to say. Okay, so we can just append whatever we want to in our list. So we talked about the append method. This is an example that I gave because this is probably the most common tool that we use with lists. Usually we create so often we create an empty list that we intend to append elements to. So this is just a really common thing to do. And I talked about mutation. So one thing that I want to point out here, and this might kind of seem like a given, but if you think, let's think about this, right? Like there are several ways that this change could occur, right? If you were making a decision, if you were writing the Python programming language and you were making a decision about how this change should occur, let's look at the ways that it could occur. One is that one way that this change might happen is if we if we got a different version of the list when we called append. One thing that would be possible, hypothetically, is that it would give us a different version of the list back with that element appended into it, right? So you'd have this empty list in your memory, and then append would say, oh, well, this list is now equal to, here's a new list with that element added into it, and it would like displace it somehow. Another way would be to literally alter that empty list to contain the word, or to contain the element being appended. And the first way describes what we would call immutable behavior, and the second way describes what we would call mutable behavior. So mutable behavior means that the value changes, but the object doesn't change. Immutable means the only way for the value to change is to get a new object. The value never changes, but you can get a different version of the same object, just with some different version of it with something else added onto it or something. And that concept might seem like really particular, like why would I even explore that? But it's an important concept, and mutability is something I'm gonna kind of harp on a little bit, because it seems like easy to ignore, but the ramifications of not understanding it are kind of severe. So I'm just gonna keep mentioning it, and if you have questions, feel free to ask. But it'll become clear when we talk about tuples exactly why I'm making this kind of juxtaposition. Cool. So lists have mutable behavior. So a number of these methods cause mutations, right? So append causes a mutation, clear causes a mutation, copy doesn't cause a mutation. It's not a mutable method, but it's only useful in the context that lists are mutable. And we'll talk about that in a second. Extend, insert, pop, remove, reverse, and sort all the ones I highlighted cause a mutation in the list. So count and index are the only two methods for lists that don't actually cause a mutation. And all of these, plus there's one other thing that's not a method that causes a mutation in the list that isn't represented here. And it's item assignment, and I'll just take a note to cover that. Item assignment or reassignment. This is a mutable operation that just happens to not be a method, and we'll just look. It'll be pretty natural. It's a lot like, it kind of relates back to indexing, so don't be too scared. Cool. So the reason I'm mentioning this is every time you learn a new data type, think, is this a mutable type or an immutable type? If it's an immutable type, you can view all of the methods basically as functions. You know, they take in values, including the type that they're called on. You know, this is, for all intents and purposes, essentially an input into this function, right? I know I'm saying it's a method, but methods are very much like functions, right? So list.append hello, list essentially is an input into the append. It's just that visually it doesn't look like it's an input in the same way that the actual object that we're appending looks like it is. So if for immutable types, their methods, you can just think about them as taking inputs and giving back returned values, just like any other function. For mutable types, you have to remember which methods cause a mutation and which don't. And if you think you can get away without doing that, then good luck. That's fine. That's fine. I mean, some of us have to learn the hard way. I know I did. So no shame if you have to learn the hard way too. I absolutely had to learn that the hard way. So, yeah. Anyways, let's just keep going on with examples. So clear. We'll just run our code again. So you can see we start off with an empty list. We append some things to it. And then let's say I want to just clear out all the contents of the list. I can say list.clear parentheses to invoke it and print list. And we've got an empty list again, right? I was going to demonstrate this and then I kind of got sidetracked. So if I print off the IDs of these, an ID is a unique number given to a unique object in Python, right? So this this is going to prove my point about this being changes to the same object, right? So we didn't get different objects. Oops. These are always the same objects. And we can tell because their IDs are the same. We get the same ID every single time. Even though the value has changed, the ID has not changed, right? Let's do this. I'll do this. Print off the ID and then the list, the value. There we go. So we have empty list, we have a list with contents in it, we have an empty list. You know, if at any given point, you know, we compared this list equal in value to an empty list, you know, this would be false. So these are not equal in value. These are equal in, well, they're not equal in value, but they are the same object, right? In memory here. I know that's kind of a lot, so it'll make sense eventually. Okay, cool. Copy. So since we can change the value of a list, that has some pretty extreme implications if you think about it, right? Let's say I have some list in my program, and I pass it to, and we'll say my function takes in some list, and let's just say it clears it. And then returns okay. So look at this bit of code. So I have a list. I pass it to a function, and the function takes in some list. It calls clear on some list and returns it. So all it's going to do is return an empty list. It's not that interesting of a function. So look at this code, and let's think about two questions for this. So what do you think it will do? Specifically, what do you think the value of list will be if I print list after I pass it to this function? So what's the value of list? Yeah, so let's think about it actually, like what's the value of list, and what should be, right? So think about what what you think this will do, and think about what it should do. Maybe you think it should do what you think it will do. I moved it. Whoops. Okay. Oh, that's from before. Dang, sorry. Is that what pops up in if else? I don't understand the question about if that's, is that what pops up in if else statements, but okay, so we've got a question, isn't some list and list two different variables? This is interesting. I'll answer that in a second. So I'm assuming people are kind of, I'm not seeing too much activity. I see a couple people putting in answers here. Yeah. So I'm seeing a lot of empty list, and I'm assuming that's in answer to the first one, that the value of LST will be an empty list. And what do you think? So let's shift gears here. So that is true. This code will clear out list. It will do that. And I know this is a leading question, but I think it's worth, I want to ask it because I want you to think in these terms. What should it do? Like what is, I mean, you know, the truth is it should do this, but, you know, like what is this desirable behavior? Do you want to write code that, you know, do you want to write functions that that alter their inputs? Like what, I want to ask this question. I mean, I think it's obvious by the way that I'm asking it, my opinion on it, you know, but I want you to think about it, like in terms of, ask yourself, like what are the ramifications of writing code like this? If I just wrote code, wrote functions that took in lists and then altered those lists in some way. You know, what are the ramifications of that? Is that a good thing? I mean, maybe you're like, oh yeah, you could do all sorts of things. I mean, you could, you know, or are there other ramifications that you can think of that for doing that? Let's see, we got a couple questions here. You do not want to have functions that change your inputs. You might need to use the input still elsewhere. Okay. It mutates the input of the list. It could corrupt the data. You'll lose your original data. You need to make a copy of that list. Yeah, exactly. Cool. Yeah, so we'll kind of move on from this. You know, and I know this is, we will only have a few answers in here, but hopefully everybody's thinking about this. And I I want to kind of create this kind of thinking. I want to encourage this kind of thinking, like, you know, if I adopt some pattern, you know, this pattern, this is a pattern, what are the ramifications of that, right? And this is all good thinking. What I'm seeing here is a lot of good thinking. And if you have another answer, you can put that in, uh, uh, and as you know, go through and read everybody else's answers, and try to get some variety of thought in here. So, general consensus, and I am of this opinion, is that this behavior is undesirable. This is not what we want to be doing. We want to write functions that have, don't mutate their inputs. Somebody asked, like, aren't list and SUMList two different variables? So, I mean, list is formally a variable. LST is the identifier of that variable. SUMList is technically a parameter. That's technically what we call it in this case. SUMList, the word SUMList is the identifier for that parameter. So, you know, I don't mean to be pedantic there, but you might. I think the question is asking, aren't these different things? Like, why should one have to do with the other, right? And I think that's a totally reasonable assumption to make. Like, why should, you know, if we're clearing SUMList, why does that affect LST, right? That's a totally reasonable assertion to make. It doesn't look like this is clearing list. I didn't say list.clear, did I, right? And I want you all to notice that you will make assumptions like this, and just that's fine. I do this kind of stuff too, and it occasionally leads me astray, but get in the habit of checking that and verifying that. We could do something interesting here. We could print the ID of, let's do LST. Oh, come on. Oh my gosh, I'm hitting all kinds of keys. Let's print the ID of list, and then let's do the same thing with SUMList. I'm actually do the ID, sorry, the ID first. Then that way they'll be kind of in line. Okay. So these are the same ID. Python, like, these are two different identifiers, but in this case, they refer to the same object, right? So that's what makes it weird. So you assuming that these are different variables, like they're different identifiers, but in this case, the way I wrote this code, they will refer to the literal same object in memory. And for an immutable type, who cares? It's immutable. You don't have the problem of being able to alter the value on the data type level. So who cares, right? And that's how it is with passing an immutable value into a function. Like, it's going to have the same ID, but it doesn't matter. With a mutable value, it does matter, because you know, now you've just handed it off to something that can change it while not seeming like it's changing it, and that's where the danger comes in. So, okay. All that to say, SUMList equals SUMList, and this is what I generally like to do, .copy. Now, some people will say, you know, some people I think prefer to change the variable name at this point. So maybe they would call this like some other list equals SUMList.copy. That way you technically have access to the copy and the original. And there's times when that's okay. There's times when I use that to my advantage. We'll kind of get into that later. But in general, you don't need access to the original. In general, you can just override the identifier with a copy of itself. And this will work in a way where it's not going to alter the original value. So notice list and SUMList now have different IDs, and this is what the function returns, which is that empty list, and then this is the original value of list. Cool. Okay. Oh no. Sorry about that. Okay. Okay. Let's look at another one. So another thing, every time we look at a new method or a new function, or even a new like operator, we can. I want you to keep track of what it does. I'll give you a little schema: input, process, output. And I think I've gone over this in class before. IPO. There are other sort of more nuanced schemas. There are different ones that you'll hear, but I like this one. It's simple and kind of covers the bases. I'm usually I'll ignore process, and I'll kind of use each of these a little bit loosely for different situations. But for things that feel like an input to me, I'm going to think of as input. For things that feel like an output, I'll use as an output. For these, I wouldn't consider append to have an output. And I forgot to mention this, but if I print off the result of append, what do you think append returns? I know this is another very leading question, but I want you to think about it again. What do you think append returns? Does it return the original list without the value appended, or does it return the list with the value appended, or does it return something else? Go ahead and put it in Slack if you know or if you have a thought. You don't have to know. Like, tell me what you think. I'm actually interested. If you know, then great. But I want to see what your intuition tells you. That's what's more interesting to me. The list with the value appended. List with the value appended. Yeah. Okay. Anybody else? Any dissenting opinions? We got a question. I'll take this question here. Would list and SUMList have this? Oh, I think I answered that. About having the same IDs. Yes, they will have the same IDs if you don't copy them. SUMList is a placeholder for whatever variable you input. Yeah. Whatever value you put in there. Yep. This returns the same list. Yeah, okay, so it seems like we're getting some consensus on people's intuitions, and this was definitely my intuition when I was learning about this kind of operation, is that, oh, well, I've been learning about functions. Methods are like functions. Functions have inputs. These have inputs. They have outputs. Functions have outputs, so methods have outputs. Methods can have outputs. For mutable methods, most mutable methods don't have what we would consider outputs. So the result of append, you ready, is none. So append returns none, which we think of, technically, yes, it is an output. It is returning the value none. All functions need to return something. If no return value is specified, then none is returned. So append does return none, but this obviously has nothing to do with the list or the append operation. So notice we don't recover the value, we don't recover the result of the append by saying, oops, gosh, I keep hitting that scroll up and down key. We don't do this. We don't say list equals list.append. In fact, this is like saying list equals none, right? Because it equals whatever append returns none. Right? So That's an important thing to remember. Most mutable methods don't return anything. Or return none. Which I'm sorry, that's kind of confusing. When I say don't return anything, that means they return none. So yeah, that's the case for most mutable methods. So anytime you learn a new method, do this IPO thing and like kind of create a little, I think it's like a little mantra that kind of goes through your head to help you memorize how each method and each function works together. You know, the memorization is never really like the best part, but in this case, giving some sort of structure so that, you know, more or less with some simple set of rules, you know, okay, if I remember the inputs, the process, and the output, and when I should care about the output and when I should care about the process, then that'll help you remember everything. So with append, I would say, you know, the input is the list in that it's a member of the list class. So I would say append is a member of the list. Its inputs are any arbitrary object to be appended to the list. So that's, I'm remembering its input as the type and just a description of it. So I think about the type and the description for input, process, and output. The process in this case I would consider to be the mutation that it causes. That's part of the process of an append. Whatever append, however it does that behind the scenes, I don't know. I don't particularly care. All I know is that it changes the value of the list, right? And then the output is none. The output is what it returns, so that's none. Cool. So let's do this with count. So count is a list method. Takes any arbitrary object to be counted in the list. Its process, I don't care about the process for count. Process is an immutable operation, meaning it does not create an immutation. So its output is an integer representing the number of times the past and input occurred in the list. Representing the number of times the past and input occurred, count. Representing the count, oh my gosh, I keep hitting that scroll button, dang it. Okay, representing the count of the input within the list. Cool. So I would do something like that for count. So every time you learn a new function, kind of keep that in the back of your mind. And I'm not going to write these out for each of these because it just takes a little bit, and I'll spend the time focusing on giving examples from here on out. Okay, so count. So let's do, just have a list equal okay. So if I print list, now since this returns something, I can count, or I can print it. It makes sense to print it because print will show me the value returned, essentially. Okay, so list.count of 33. There's 133 in there. Let's see how many 44s there are. Looks like there's 2 44s. Let's see how many 77s there are. There's 0. So if I try to count something that's not in the list, the count of that thing is 0. It didn't show up at all, so it's 0. So that's count. Let's do extend. So extend is another mutable operation. Extend is somewhat similar to append, Um, and I've seen people do this where they need to append multiple things. So they'll do, and it seems really rational to do this. It just happens that Python doesn't support this. So I can't append multiple things. If you find yourself wanting to do this, just do extend and then pass a list with all the things that you want to add. So this will extend is just really a multiple append. It just says append all these things. Now, I wish that append would just support like multiple elements in it, and it would kind of make this a little easier. But that's how it works. And then if I try to, let's print list and see the result. So you can see we got 333 and 444 extended onto the list there. Index, this is another immutable one. So list.index of 55. Let's do 55. So I can see here we have 44, then 55, which is index 0, and then index 1, so that should be index 1. Oh, I was like, why didn't I see anything? Because I forgot to print. It's index 1. So let's see what index 44 is. Now I've got multiple 44s in here, so this is a little confusing because it shows up in here multiple times. Does it give me the first one? Does it give me a last one? Does it give me a list of all of them? And it gives me the first one. So that's the behavior of index, and that's just worth remembering. Index, so if I was going to do IPO for this, I'd say index is a method of lists. It takes in an object that is in the list and returns the index of that object. It raises a value error if that object is not in the list. And it returns the first index as it returns an integer, which is the first index of the occurrence of that element if it's in the list. Cool. We've got a question here. So is using extend the same as concatenation with the plus sign? It's similar. Yeah. You could actually, one of the way that I really prefer to do list manipulation stuff is generally, and I'll get into this when we get into tuples. You don't actually need any of these mutable methods. It's kind of funny. You can do it all with concatenation, slicing, and indexing. But this will have the same effect. So list plus equals some other list with multiple things in it is in effect an extend. I prefer list manipulation with these, like with concatenation, slicing, and indexing over the methods. The reason I don't teach it is because it's not conventional. I think it's Pythonic to use the built-in tools. To me, concatenation, slicing, and indexing are like three simple and very obviously related tools, and they're simple systems on their own that relate to each other in like kind of magical and like powerful ways. And if you master that system, the world is your oyster, for at least the world of list manipulation is your oyster. So I prefer to do things that way. In my own code, I'll do things that way. But I teach the methods because we cover the methods because A, that's what you'll see, and B, that's more or less what people will consider Pythonic or the correct way to do things. Yeah. If you can understand these things through concatenation, slicing, and indexing, then that's great. I won't discourage that at all. That's a good question. Okay. Insert. So insert is, it's kind of like, I think about it categorically as similar to extend and append, in that it adds an element into the list, but it also allows you to choose where you want the element. So if I want this, if I want to prepend it, I can do list.insert at 0 with, let's just do hello. And we'll just print, oh my gosh. So I get to choose where I want this element placed in the list. I think everybody's super excited to learn insert. It's like, whoa, you know, the power, the limitless potential, and then like you never use it. It honestly, I'm not saying you shouldn't know it, but you don't. I just don't find myself using insert all that often at all, really. So cool. So let's look at pop. So pop is a weird one. It's a mutable method, so it causes a change in the list, but it also returns a value, and it's really weird in that it does both. I don't know of another method that does both, but pop always does both. So if we do list.pop, and it can take an argument. The argument is optional. If I don't pass in an argument, it's just going to pop off the last element. So that's 99. If I do give it an argument, the argument is an index. So 0, 1, 2, that'll pop off 33. And I should be actually also printing off the value of the list so we can see how the list value changes, right? So 33 is returned by pop and also removed by pop. And there 99 is removed. So you might look at pop and say, oh, pop removes an element from a list. That's useful. So what the heck does remove do, right? So the difference between pop and remove is, one, remove doesn't return anything, and it'll kind of hopefully make sense why in a second. Really, the difference is the input into the function. So pop takes in an index and removes and returns the value at that index. If no index is given, it assumes an index of -1, which is the last element. Remove takes in an element and removes the first occurrence of that element. So if we do list.remove, let's do remove 55, and then let's print list. And you can see we had 44, 55, 33. In our output, we got 44, 33. So let's do 44 now, since we have multiple 44s in there. So notice it removed the first instance. It removed this 44, but not this 44. So if I want to remove the next one, I got to do it twice. And I'm pretty sure, I think, let's try this. I'm going to actually get the help docs, because I forget if there's a flag for remove. Oops. List.remove takes in self and value, removes the first occurrence of a value, raises. So it raises an index error. This is something I've been meaning to include more, and I've been forgetting, so apologies. It's important to keep track of what errors a function will throw as well. So this says raises a value error if the value is not present. When I say it's important, you know, what's more important than keeping track of the values is or of the errors is being able to read and handle errors as they occur, and not being afraid of them when you get them. So by that virtue, if you get a lot of errors while you're coding and experimenting and running your code a lot and like letting it get errors, you will just from experience, you will learn what circumstances lead to what errors, just from experience. Cool. All right. Reverse. So reverse. Anybody want to guess what reverse does? Big surprise here. It reverses the list. So notice we got 99 to 44 there. And then, of course, if I call it again, I'll reverse it back to the original form. And then sort. Is going to sort the list. So this will sort in ascending order, so you can see 22, 33, 44, 44, 55, and 99. So if the order of the original list was important and you sort it, that order is gone forever. It's not going to come back. You can't reconstruct it. It's not like there's not an unsort method. So what I generally recommend, the more useful tool is the sorted function, SORTED function. You can do list. This does not create a mutation in the list, so I prefer it in almost all circumstances. Print the sorted list, and then we'll print the original list. So I can grab the sorted version of the list anytime I wanted by just getting the output of sorted. There is a potential in very large data sets, if you're sorting something that's huge. I mean, there's the overhead of sorting it in the first place, and sorting algorithms, as some of you I assume know, their efficiency, depending on the algorithm, can change depending on the size of the data set. So there's that whole aspect of it. The only potential downside to using sorted is that it gives you a different object in your memory. If this were like several million records or something, there'd be the, whatever overhead of sorting it, and there'd be that overhead whether you're using the dot sort method or the sorted function. But now, if there were 10 billion records, now there's 2 billion records that are kind of duplicated. So there's a potential downside to this. A lot of times that just actually isn't a big deal. Things have to get pretty big before you really have to worry about like kind of running out of memory. Even a netbook these days has like 8 or 16 gigs of memory. I've got this like super light little computer with 40 gigs of memory in it, so I don't know. I'm not really worried about overloading my memory as much. So, but it is a potential consideration. So keep that in mind if you're working with something that's very large. Probably the bottleneck is just the sorting algorithm and the time it takes to sort something that large anyway. So. Which is the same whether you're using sorted or sort, like I said. Cool. We've got item assignment. We haven't taken a break yet. Apologies for going over time. Let's reconvene at 20 after the hour. All right, we're back. So just have some more of the functions for us to go through here. Okay, cool. So we'll talk about some of the other things. So those are the methods. Let's talk about item assignment. This relates back to indexing. It's like assigning to an index is another way of thinking about it. Also, if there are any other questions, feel free to put them in. So if I say I've got this list here, and let's say I decide index 2 here should be poodles or something. So I'll say list sub 2 equals banana. Oh wow, I unironically can't see how many N's and A's there are in there. I think that's the right amount. Dyslexia is a real thing. All right. Cool. So let's print list. Oh. Now, so you can see I overwrote. Let me clean up all this nonsense here. Gosh. I think that's everything. Yeah. Okay, so you can see that I overwrote that third index with a different value, right? So this is a mutable operation. If I do the ID of both of these, same ID, different value. So this is a mutable operation that just happens to not be a method, right? It's sort of the only outlier in that regard. There are like there are other operations like that concatenation thing that is actually a mutable operation, and but you can do the same thing with a method is what I mean in that particular case. So there isn't an analogy to being able to do this in a method in Python. It's just item assignment like this, and it's worth knowing. Okay, so let's look at some other functions. Len is a good one. Len is a very, very useful one. Use len all the time. Len list 6. So 1, 2, 3, 4, 5, 6. So there can be some confusion about indexing starting at 0 and len giving you the length as if it were counting from 1, right? So len doesn't tell you the maximum index. It tells you the number of elements as if you were going to count starting at 1. So 1, 2, 3, 4, 5, 6. There are 6 elements. The maximum index is 5 because we have 0, 1, 2, 3, 4, 5, right? So there can be some confusion about that, but I just wanted to clear that up. Len gives you the proper length as if you were counting from 1, not 0. You can always recover the maximum index. So we could say max idx equals len list minus 1. So the highest index is always the length of the list minus 1. It's just 1 less than the length of the list. So this is but one of the many uses for len, and you do use len for this. There's times when you want to know the maximum index of something, and you can maybe you can use that to index into some other list or something. I don't know. Who knows? Sum. Let's look at sum. So sum takes in a list of numbers. So I always think this is an interesting one because this when I really got it in my head about how sum worked, and I was thinking about how did this happen? I had a long time ago when I was first learning an epiphany around this. Like the input type of sum is a list of numbers, right? So this helped me think about how to think about specifically lists as types, and this applies to other types as well. But we don't think of the type of a list as just the list. It's a list of some other types, right? Potentially mixed and matched types. But if we mix and match types that aren't numbers, we could mix and match ints and floats, but we couldn't put any strings in here. Even if this was a string of 44, this is going to yell at us. It'll give us a type error. It'll say unsupported operands for plus between int and float. So it's saying it doesn't know how to add an integer to a string. And that's fair. I don't really know how to do that either, so I don't know what it should do, so probably an error is the best thing. But if you have all numbers, and like I said, we could mix and match some floats in here. We could have all ints, all floats, mix and match ints and floats. Then we can get the sum of those. So sum's a really useful one. Sum and len together, so sum over len list. Anybody know what this is? Yep, that's your average. So sum over len is your average. So yet another of the very many uses for the len function. You wouldn't think such a simple function would get so much mileage, but you'll be using it all the time. Cool. All right, so let's look at max. Max and min. I'll just talk about these together because they go together. I mean, you can kind of guess what they do. This is going to give me the largest and the smallest element from here. Okay, so I've got a list of strings. What's it going to do for this list of strings? So tomato is clearly the max of this list, and banana is the min. Of course, right? I mean, makes sense to everybody, I assume? No. I don't know why max and min. I mean, I do know why, but I understand mechanically how it works, but I don't understand why they made max and min have this behavior. This might be sensible behavior, but I don't know why they conflated it with these functions. But that's how it works. So it's not it's not clear here, but what's happening is max and min are referencing the ASCII values, the ASCII and Unicode values. Yeah, it does. Yeah, so it'll so I think T is the U, V, W, X, Y, Z. Yeah, so T is the closest to, I think if we had zebra, I think that would be our new max. Yeah, so it'll basically tell you how far down the alphabet it is. So, I mean, there's uses for this. I'm not saying it's not useful or that behavior shouldn't exist. I just think it's weird that it's in max and min in particular. String methods would have made more sense, or just like their own functions, but This is what they decided to do. Whatever. So now you know if you need that behavior, it's built into max and min. Cool. Any and all. So can I? A while ago we talked about truthiness and falsiness. Give me a thumbs up or a thumbs down if you remember, if you have a sense of truthiness and falsiness. Question, does it use the first letter ASCII code or the sum of the ASCII codes of each letter? I think it does. Well, it'll take in multiple letters. I mean, basically it'll alphabetize them. So like ZZ would be more of a max than like ZA or something. You know, so I don't think it's the sum of the whole thing. Actually, you know, now I'm curious. Let's just throw a bunch of Z's in here. Oh, well, of course it's going to be that. But let's see if we can get tomato to outmax that zebra there. Yeah, so I think it's going to be more or less like the first letter. Okay, so I'm seeing all thumbs up for truthiness and falsiness. So I'm going to speak now or forever hold your peace, but I'm going to just assume some working knowledge of that and not cover that concept again, because no need to. Okay, so any and all, let's just do these. We'll do these ones. Any, all. So, well, these aren't that interesting anyways. Any is going to return, so both of these will return true or false. Any returns true if any of the values in the list are truthy. And returns false if no values are truthy or if they're all falsy, right? So if I had, gosh, excuse me, get hiccups at the worst freaking times. 0, empty string, empty list, 0.0, I don't know. I'm done thinking of falsy things. So falsy, right? And then all returns true if all of the elements are truthy, right? So if I have hello, right? So any's going to be true because, you know, any of the, at least one or more of the elements is truthy, and all is going to be false because at least one or more of the elements are falsy. Enumerate. Enumerate is a very useful, I know I keep saying this. I feel like I'm just like, oh, this is so useful. Oh, this is great. This one's great. You're going to need this all the time. I feel like a broken record, but I mean, I also stand by what I'm saying, so, you know, maybe I should shut up. So enumerate's really useful for for loops in lists. So let's say you're solving a problem. There's a problem like this in Learn. Some of you may have encountered it already. Let's say I want to write a function that raise to index. Takes in a list, and let's call this my list. I don't have to rename this since this is a global variable and this is a local parameter. Like, these two are essentially unaware of each other. But I just for the sake of clarity, I like to just give it a different name so it's clear and definite which one we're talking about at any given time. So. Mm, mm. Okay. So the goal here is to return a um, a list, and I'm going to just call it accumulator. We talked a bit about accumulation, so we'll make a list accumulator, and I'm going to return that accumulator, ACC. And I suggest, by the way, when you solve a new problem, um, this is a good starting place, right? You want to get to this as a boilerplate. Like get in like at least one call to the function so you can test it and just run your code a bunch and test it. Have some test data, make some assertion about given that you pass this data in, what do you expect to have returned? You know, I'm not going to do the calculation here, but I know, so in my head what I'm thinking is I want to return a list where each element is the squared value of each element from the input list. Excuse me, not the squared value. Each value is the result of raising each value in the input list to the power of its index, which is going to be, we're going to get some pretty big numbers here. Okay, so we're going to say for, we could say for num in list ACC dot append num to the, oh, come on, num to the what? So to the index. So how do I get that index? Anytime you're writing a for loop, you've got a list and you think, oh, I've got the element, I need access to the index. The answer is always enumerate. All you need to do is enumerate. So even if you have that thought, oh, I think I might need the index, just enumerate. Just throw an enumerate in there, and that'll give you the index. So notice, this gives me the opportunity to name two identifiers in this for loop. So I get to name not one, but two identifiers. So the first one is going to be the index, and the second one is going to be the number. By convention, we'll call the index I or IDX or something. I always like to use IDX. It doesn't have to be. Again, this could be peanut butter or something. Like you can call it whatever you want, but obviously probably better to call it index than peanut butter. So I'll call this index and I'll call this num, and then this is the element. This is just ELE, whatever you would normally name it. Anyways, okay. So let's see what we get. There's our answer. Looks right to me. So 44 raised to the 0th index is going to be 1. 55 raised to the first is going to be 55, and then all the rest. Cool. So yeah, there are quite a lot of situations where you're going to be looping through something and realize that you need the index. And this will work for a string as well as a list. Anything that you can loop through, you can enumerate as well, and pull out the index as well as the element. So it's really good for that. Sometimes you don't want to think about it like an index. Sometimes you want to think about that number as like maybe a count. Maybe you're counting in a one-based way, like positionally, rather than in a zero-based index. So you get to say where you want that index to start. You don't get like a stop or a step parameter, but you do get to say what number you want it to start at. So let's just say I wanted it to start at like 20, which I don't know why I would, I could do that. And then my first, I'm going to get this huge list, right? So 44 to the 20th power is whatever that monstrosity is. I know you all were curious, so. And then etc., right? So let's see. Oh, where am I? Usually, probably where you want to adjust it is to like 1 or something. So it's not uncommon to want to start your enumerated index at 1 or something, and then oops, and then the first element would be raised to the first, the second would be raised to the second, third to the third, etc. So this is a little bit weird. I always find this a little weird because, like, if I were writing Python, I probably would have laid it out like this. I think it makes more sense for the index to come after, and then you name the element and then the index, and then the arguments are the thing where the element comes from and the place to start the index. Unfortunately, it kind of feels a little messy. It's the way they designed it, though, and you get used to it. So I know I critique Python a lot. I absolutely love this language. It's not perfect, but it's great. So yeah, so you have to remember that ordering. Whatever you call the first thing is going to be the index. Now, sometimes it's easy to do this thing, and I've even been caught off guard by this. And this is a really weird error to debug because it's valid code that looks correct, and like all the pieces seem to be in the right order. It's just that I called this num, but really it's the index. So num now has the value of index, and idx has the value of num. They're just swapped. So this is a problem of bad labeling, not of bad logic, right? So just make sure you remember that the index comes before the element, and that in the input, the starting index position is the second argument, and it's optional. So, all right, that's index. Parallel lists. So we're going to talk about parallel lists, and I'm actually going to go into, oops. Unpacking nested lists. Is that all we got? Okay, good. So two lists that have equal length and contain associated values across their indices are considered parallel. So I think I've given examples about this. I know I have in study hall recently. So let's just do names equals list. We'll say Sally. Jeff. And Billy. I don't know. And then we'll say ages. 33, 66, 55. So if I want to go through here and like print off, each person's name is age, years old. There's a couple ways that I can do this. I can say for, we'll do the range way first. We'll say for I in range len names. And then I could print, I'll use an F string here, print name, oh, excuse me, names sub I is age, ages sub I. We'll just run that. So Sally's 33, Jeff is 66, and Billy is 55. So this is one way to do it. The way I prefer to do it is there's another function, my favorite functions, it's so useful for this particular task, zip. It makes dealing with parallel lists very nice. And then I just get to name in here like I would with enumerate. I get not one but two identifiers that I get to create. So you may be able to guess names is first in zip, then followed by ages. Fortunately, they come out in a sensible order. So name first, then age. Now, usually when you're dealing with parallel data like this, you're just dealing with two lists. Sometimes more, though, occasionally more. So you can zip as many things as you want. If I could zip something and then foo or whatever. So I could just keep adding lists to zip in, and I would have to just keep adding identifiers to represent that data. Now I can just do there we go. Sally's 33, Jeff is 66, Billy's 55. Unpacking. I'm going to skip this stuff on unpacking because it's confusing, and it literally, A, it never comes up, and B, it's not useful. So if you want to read through that stuff, the materials on the GitHub repo, it just is not, it's a feature that just kind of we don't really need to go over. Cool. We're running real lean on time, so we're not going to get through everything today. That's okay. We will get through everything as class goes on. It'll all come back together eventually. Okay, so let's change gears into while loops. Yeah. So we talked about for loops. I'm assuming it seems like people are feeling good about for loops. Like it's making sense, which is good. So I'm going to kind of use this as a basis to understand what a loop is, right? So let's just take another list. So ages. I want my other list. Why? I don't know. But I want it. There we go. Okay. So for element in list print element. So a loop, a for loop is a loop, a while loop is a loop. A loop just runs some process in a linear fashion. That's what we think of as a loop. Some of you may have, I'm presuming you've heard of, everybody's heard of like parallel processing and things, and I think there are some ways potentially that loops can be optimized like under the hood to like automatically take advantage of parallel processing. The advantage that they can take of parallel processing is somewhat limited, just that the computer can infer for you. And I'm not sure that Python, that any implementation of any Python loop actually does. I think actually that they don't. They run in a single threaded way. So there are multiple ways that we could think about iteration, right? We could think about, if you have some repetitive task, given a certain problem, it may or may not be feasible to offload that task into parallelization. But loops don't, whether or not they do that at all, they don't do that to a great extent, at least in Python. And we don't think about them that way. We think about them as like having a serial execution, in series, one after the other. So, yeah. So this is just a regular loop. We're just going to do our process for every element in this list. That's what a loop is. Okay, so let's do something similar with a while loop. So a while loop is similar to a for loop in that it is a loop, but it's also similar to an if. So an if takes something like let's just say if 44 in list print something. So if takes a condition after it, and if the condition is true, it runs the consequent. Otherwise, it moves on to any elifs or whatever. So a while loop does something really similar, except at the end of the block, where the if would just move on, a while loop comes back up and checks the condition again to see if it's still true. And if the condition is still true, it'll run the code again. And then it comes back up and it sees, is the condition still true? And if it's true, then it'll run the code again, and it'll come back up and check it until the condition is false, and then it stops running the code. So it's weird because it's a loop, but it sort of bears a lot of resemblance to an if in that it takes a condition. Sometimes we call whiles conditional loops. So we could do this. Let's do this. 22. So while 22 in list, let's do this. Let's say I equals 0. And we could say I plus gets 1. We'll do that at the end in this case. And then I'll use I as an index. I'll say list sub I. So I guess say if list sub I equals 22, list dot pop I. Yeah. And then let's just print list. Okay. So this is a while loop that's being properly controlled. We got to this print here. So that means everything went according to plan. So what if I forget to add 1 to I here? It doesn't look like it, but it's in an infinite loop. So let's actually kill that process and let's see what's going on here. Let's print I. So I never incremented I. So it looks like it's just a wall of steady zeros, but I'm trying to like select those, and you can see how fast it's going. And if you were here, you'd be able to hear my actually it may be coming through in the recording. Yeah, you can hear my fans kicking on. Getting into that infinite loop. I can feel my CPU getting a little warm under my hand, even from that. So it's really easy to write while loops that get into infinite loops. Remember, a condition is any expression that evaluates to true or false. So we can do while true. This will it's like throwing a brick on your gas pedal and just keep going. Let's do I plus gets 1. And I just want to do this to give you a sense of how fast this actually goes. Okay, so this is an intentionally infinite while loop. Although I promise you, you will do this by accident many times. I do it by accident sometimes. Okay, let's go. We're already 10,000s, 40,000, 100,000, right? So it's going. There's like a lot of CPU power going into this thing. If you do this on Replit, it's likely to crash your Replit for a minute, and like you'll have to just reload the screen, stop the process. That can always be a little fun. So they're better about it than they used to be. Sometimes it would just like totally wreck that Replit. You'd have to just start a whole new Replit and just abandon that one. So that hasn't been the case for like over a year. So I think they got on top of that. Cool. Yeah. So while loops, they're simple, they're raw, they're very powerful, and I'll talk about where they're applicable, where for loops aren't in a second. But hopefully you can see, like, it's on us. Like a for loop, I just write a for loop. If I did the syntax correctly, it's just gonna run my process in a nice clean way. Everything's gonna be, it's gonna stop when it reaches the end of the list, right? Nothing is a given with while loops. It's on us to control the thing, to stop the thing. So generally, what you'll have is not all while loops will look like this, but a lot will. You'll have something that changes its value, something that moves, something that's mobile, and something that's static. So while I less than 10, right? So 10 is constant, 10's not going to change, I is going to change. So while I is, actually I said less than, I put greater than. While I is less than 10, we'll increment I and print I. And then this will limit it, like this. So if these are harder to use, and if they're prone to infinite loops, and like managing them incorrectly can lead to infinite loops and unexpected behavior, like why ever use them? And the answer is you should never use them if you can use a for loop. But there are certain cases where you can't, or where it doesn't make sense to. So the cases are if the number of iterations needed to solve a problem can't be known until the first iteration completes. So I'll say that again. Let me put it differently, actually. If you can determine you have a problem that you're solving, and you've determined that an iterative solution is necessary, and if you can determine from before any iteration starts how many iterations need to take place, then you can use a for loop. So if you know or can determine the number of iterations before you start looping, then you can use a for loop. If you can't determine that, then you'll use a while loop. Yeah. So I want to give just a real quick example here. We'll say def is prime. We'll take in n, And I'm just going to write a quick isPrime function. If n is less than or equal to 1, return false for I in range 2 to n over 2 plus 1. Make that an int. If in mod I equals 0, return false. If n mod I equals 0, then I is a factor of n. We know that I is not prime. If we make it through the whole loop without returning false, we'll return true. Okay, so this problem I can use a for loop for, because I know I don't need to check every number possible. I just need to check every number between 2 and n. And I actually, I could write this so that this range is more optimized and I'm checking less numbers, but this is a good, quick isPrime function. It'll work, right? So I know that there is some number of iterations. I've already determined, n determines for me the number of iterations needed to solve this problem with a for loop. Okay, so what if I want to find the next prime number? Def next prime. We'll take in n, and so this is going to take in a number, and it will return the next prime number. So 13 is a prime number. If I pass in 13, I don't want it to return 13, I want it to return 17, which is the next prime number. The problem is primes, as I'm sure most or all of you know, follow an irrational series. So from any given point, unless we're just like referring to a data sheet of prime distances, we don't know the distance between any two prime numbers. And the only way to find out is to just go through each number and to see if it's prime. And we don't know how many numbers we need to check until we've done it, until we've checked all the numbers. So determining that distance, the number of iterations that would be necessary, is literally just doing the process, right? So what I'm going to do here is while not is prime n. So this is like saying while n is not prime, and I actually want to check n plus 1. We'll say n plus equals 1. Some of you might be thinking, well, won't I be mutating the global variable n? N is an integer, so it can't be mutated outside of this scope. So that's a safe operation. So this says while n plus 1 is not prime, add 1 to n, and then it'll check if the next value of n plus 1 is prime. And if it's not, it'll add 1 to n, and just keep doing that until one value is prime. So once is prime, n plus 1 returns true. Not true is false, so that stops our loop. And then we'll return n plus 1. And that's our next prime function. So I need to use a while loop for this. There are ways of like, you can import there's an iteration library. I'm blocking on the name of it. It might be just called iteration. You can use a tool from that and like bend a for loop to your will, but you're literally just turning a for loop into a while loop, right? So within reason, there really isn't a way to solve this problem with a for loop, with a conventional for loop like this. So I have to use some kind of system that will loop until I find a correct answer, and that's it. So this is, I always like this as an example because you have is prime, which is the perfect problem to demonstrate for a for loop. You have a very clear number of elements that you need to check. And then you have next prime, which very obviously you can't say for sure. There's a lot of really cool videos on prime distances. You can look into this. some they're kind of all over the board, you know, so you can't even reliably set like a large upper bound because the distance between two prime numbers can sometimes be really vast. So anyways, yeah, I will wrap things up there. We went a little over time, sorry for that. um, we'll be running on time in the future. Next time, before I let you go, next time we're going to be finishing the stuff on while loops, but I just wanted to kind of lay the foundation for this so that you could have some, you know, have a handle on this going forward. We didn't get into strings, but I think like you'll have a good enough foundation there, and kind of expanding on that knowledge is just worth taking a good amount of time for. So we will cover those two topics next time, and I promise we'll get caught up to where the material says we are. Cool. That's a wrap. Y'all, I release you. Have a good rest of your night, and feel free to hang out for questions if you want. Looks like we got a few here. We just stopped the recording.